What, Aditya? So let's do one thing, okay? I'll complete a part, and then in the discussion session you can have your camera on. How about that? Sounds like a plan? So that you can conserve energy. What? I don't hear from you. During the discussion session, let's have our camera on. What do you think, Dharmi?
Yes, sir. That will be better.
Good suggestion.
Yes, sir.
All right. So, what happened to the cameras that were on?
They are sharing their data, sir, for other classes.
Data. Huh? I don't understand yet. So it's becoming difficult for me to address people. It's like I don't know.
Sir, you are mute, sir.
What?
Oh, you was mute. Little.
I'm okay now.
Yes, sir.
Yes, sir. Yes.
Yeah. No. It's like talking to a bunch of inanimate objects. We call it in Tamil jatam. All right. That also there is no chat answer. Chat accessibility is very low. Is that the reason? No answer again. Only Aniket has said good afternoon.
I also said, but at that time, like it's long back.
Oh, okay. Okay. At least there is some Sarah. Tara is saying hi. You mean breakout rooms? No, yeah. When I complete a particular discussion, I mean concept, and I ask you, or I ask you questions, or you asking questions at that time. How about that? Huh? Yeah. Okay. I'll take it as yes. All right. Now, I'm assuming you don't have questions. If you have questions, mind you, you can either post it on the common WhatsApp or DM to me. Okay. You can DM to the TAs also. If you have any doubts, any clarifications, anything that you want to confirm, you can do that through WhatsApp. Okay. Sometimes if it is necessary, we'll chat on Zoom or Google Meet. Okay. Now, in the last class, we were looking at some of the structures where just equilibrium equations are enough to get the stresses in the structure. Okay, such structures are made of membranes as such. A membrane is one which which is stretchable in any direction, but does not have the capacity to take compressive stress. Okay, the one-dimensional equivalence of that is a cable. All right. So that's what we did last class. There is a lot more to it, but I'll just reserve it for your assignment. Okay. Today, what we'll do is I just want to complete one more part of it, and that is this discussion. Okay. Where let's say I have a body. Don't ask me why I'm drawing a body always like this. Let's say I have a body, and we are looking at a point P. Okay. The difference that we have here between this point P and a particle P is what? On the chat. Difference between this particle or this point P and this is what? What's the difference? What's the difference? Finally, Karthik is answering. Point P is experiencing some internal force, right? Well, point P is experiencing some force. Okay. P is outside the body, is a free point. Okay. Relative motion between itself is possible. One of them is in the body. One is on a boundary. No, not really. These are two particles. This is a particle, this is a particle. This is particle within the body, and this is a particle that is outside. But what's the essential difference? I'm yet to get an answer in that sense. This is a somebody has said free, but can you improvise on that? This is a particle that is free. Okay, free is bounded to others. It is bounded to others. Fantastic. Uh, okay, this is independent. Okay, what else? Point P, which is a part of the body, is connected to other parts of the body. Fantastic, Tara. Yes, it is connected to the other parts of the body. Or in other words, if there is an adjacent point to the left, right, up, down, whatever, there is something that is continuous. Got it? All right. So there is something that is continuous when I do like this compared to particles that are just sprayed around. There is no continuity between them, but there is continuity as far as this is concerned. We usually use a field for this, right? Where given any particular xy, I can locate a particle. Okay. With that philosophy, we did an exercise of cutting, right? We cut like this, we cut like this. Let's say this distance is very small, dx tending to 0. Similarly, we cut like this, right? This is very small, dy tending to 0. And then we took this particular simple element, which is nothing but a particle, in the sense that dx and dy are tending to 0, and then examined what stresses this point is undergoing, right? That's what we did, right? So, and therefore we revealed all those possibilities. All those possibilities and drew this. But we did not say anything about, okay, this point is a point of a continuum is something that we have not stated here. For example, if I take an adjacent particle, okay, are the stresses related to the adjacent particle? Are you with me? Are they related to the adjacent particles? If I take one more particle over here, one more particle over here, one more particle over here, let's say P1, P2, P3, P4, are the stresses that I find for P1, P2, P3, P4 related to P? That's the question that we will ask today. Okay. If they are related and the stresses are continuous, okay, then there is a possibility that I can write down equation of equilibrium for this point P, which is contained within the body. Anybody who feels that I should repeat it, I will repeat it on the chat box. Is this clear to you? So there is some continuity. Okay, so we'll make it very simple. This is a continuous body. It has stresses all around, right? If I take any particular point P and ask the question, what stresses does it experience? I can write it down, right? But there is this possibility that if I take points which are adjacent, these adjacent points, since they are connected to each other and the stress field is continuous, there is a relationship between this point and the adjacent point as far as stresses are concerned. Okay. So using that, we did that exercise in the one dimension. We are now going to do it for two dimensions. Okay. So let me draw this again. So what I have is like this. This is dx, let's say, then this is dy. The point P is here. Sigma x, sigma y. This is what we did, right? Tau xy. And then here also we said sigma x, sigma y, tau xy. Now, what's the difference between the right hand side and left hand side as far as that point P is concerned? Let me see if you have a crisp answer. Remember, this is taken from a continuous body. Okay. And I have drawn this. If you look at this side, I have put sigma x over here. If you look at this side, it will sigma x here. Okay. So if I take the adjacent body over here, that will also experience only sigma x. Okay. So this is P1, let us say. Okay. So I'll go one more step. If this is sigma y, sigma x, this is also sigma x. If I go on doing like this, I will find that the entire body will have only sigma x, sigma y all through, which is not true, right? I'm missing something. Is this clear to you? Sigma is a field, correct? Sigma is a field. So I'm making some mistake. I want to correct it, right? If one side is experiencing positive field, the other side is experiencing negative field. Correct. That's why I'm saying this is sigma y, sigma x. This is sigma x. Okay. So that they cancel each other. Similarly, here sigma x, sigma s, this is P2, okay, which is 2 delta x away from this, right? This is, let's say, dx again, this is dx again. And if I go on moving either to the right or to the left, I'll get only sigma x. In contradiction to what I may see as a variation of sigma x along this line, where I have picked a point P. So far it's clear. Is the argument clear? Right? Given that I'm not justified in drawing it like this, if I'm looking at a body which is continuous and I'm looking at stress as a field, all right? So I'm going to erase this and say, oh, okay, yes, this is at a distance x, right, from a reference. Now, while this side, the previous one had sigma x, the next one should not have sigma x. It should have sigma x plus d sigma x. Am I right? Right? In a similar way, this should be, if I move in the y direction, this should be sigma y plus d sigma y. Right? If this is a distance y from the reference. So far, okay? All right. Now I can do a similar argument for this. So just for the sake of completeness, I'm going to use tau xy and tau yx here. So similarly, if this is tau xy, this should be tau xy plus d tau xy. Similarly, here it should be d tau yx. Right now, I'm justified in saying, oh, okay, it is in the body, and there is a field which is stress field, which is continuous, right? Perhaps differentiable also, so that it is possible for me to write it in this manner. So far, so good. Is this clear? Right? And remember, the entire body is in equilibrium, which means what? I pick any point on this body. Each point is in equilibrium. Okay, which means what? I can apply equilibrium equation here. All right. So far, okay. If I apply equilibrium equation, and I know this width is dx and this width is dy, what are the equations of equilibrium I can take? So let us say this is the reference that I have taken, right? So sigma fx should be equal to 0, right? This is positive, right? And this should give me something. Similarly, sigma fy equals 0. Right? Sigma m equal to 0, we can do very similar to what we did earlier, where we will get tau yx is the same as tau xy. Okay, so I can write that also. Sigma m about origin. Let's say this is the origin is equal to 0 implies. Okay, right. This is standard. What am I doing? I am doing stress equilibrium of a continuous body. So far, so good. Now, what I require from you is look at this diagram and tell me what will be the terms that I will get over here. Okay. So assimilate it. I'll give you a couple of minutes. Assimilate it and let's write down the equations of equilibrium pertaining to each one of them. Okay. All right. Then what I'll do is I'll be able to get this P. Right. This P. I'll be able to get equation of equilibrium related to this point P over. Okay. How do I define P? X comma Y. Okay. Remember, it's a body and I'm representing any point as X comma Y. You can call it as point or a particle of the body. Okay. Well, this is what you have. You could also have, I'm going to erase this. You could also have, let's say, gravity or whatever. So you could also have the body forces over here. Okay. Bx, By, body forces, meaning if I multiply Bx with the area, I'll get the force in this direction. If I multiply By with the total area, I'll be able to get force in the Y direction due to this body force. Okay. So I have body forces. I have forces on the surface of the element that I have taken. Okay. Can you quickly do sigma fx equals 0 first? Sigma fx equals 0. Done? Okay. Who is going to help me out on camera? Who will come here, sir? Why do you want me to do that, sir? Just do whatever you can, right? Yes, Aditya? Ah, Tara is willing. Okay. Tara, tell me. Help me out. Sigma fx is equal to 0. So what are the forces? This is one force, right? This is another, right? And opposing this one and this one, right? And this one. That's all I need to take care of. Okay. Now this is sigma x, this is sigma x plus dx, and therefore I just now I need to consider only dx, right? So tell me, Tara, d sigma x. Remember, this is only stress. This acting on this surface whose length is dy. So times dy, right? Is it in the positive direction? The answer is yes, right? The sigma x and sigma x cancel out, no problem. I don't have to worry about it. The other one that takes part is tau yx, correct? So similarly, I have d tau yx times, this time the length here is dx, so times dx, all right, plus bx times Tara. Oh, Tara is gone now. Okay, bx times the total area, right, which is bx times dx dy. Is this clear to you? D sigma x, because sigma x times this length, sigma x times this length oppose each other, so that I don't have to consider over here. The only thing is that is just remaining as it is here, right? So that's what I've written over here. Similarly, the other term, similarly, is and this should be equal to 0, right? So that I already have, okay, is equal to 0. All right. Now, how do I now look at this? This is change, right? So shall I write it here? D sigma x, if I know how it is changing with respect to x direction, which is how d sigma x is changing with respect to x, and if I multiply by dx, I'll get d sigma x. Yeah, this is clear. Aditya, mute. Yeah, you want to say something? Okay, you can. Okay, is this clear? So I'm going to now erase this and put it as dou sigma x by dou x times dx, right? In a similar way, I can do this also, but this is varying in the y direction, right? So I should say dou tau yx by dou x, dou varying in the y direction times dy, right? The rest of the terms remain the same, but I notice that the area can be taken out, right? And since it is equal to 0 and dx and dy are not equal to 0, they are only tending to 0, I can now remove them. Now I have a differential equation, partial differential equation here. What do I get? Dou sigma x by dou x. I'm specifically putting it as xx so that no confusion, plus dou tau yx by dou y plus bx is equal to 0. What I get? It is not difficult for me to extrapolate to sigma fy is equal to 0. Okay. Can one of you help out for 1 mark? Who wants to help out for 1 mark? For the y direction.
Dou sigma yy by dou y plus
Dou sigma
yy
by
dou y
by
dou
dou
y
y
plus dou tau xy by
very good. Xy
dou
by
tau dou x
dou x.
plus by is equal to 0.
Fantastic. Thanks, Ashwath. Okay. There's the third equation, which is what? Moment equilibrium. Correct. What should moment equilibrium give you? You can do that exercise and you will get tau xy is equal to tau yx. Okay. So that I can now substitute. Oh, okay. I can now change this to xy. Okay. This is already xy. All right. So I can now take this off. There are two equations that I have. So far, so good. Is this clear to you? Any questions on this? Any questions on this? If you don't have questions, I'll do one more small step so that you get introduced to indicial notations also. For no loss of generality, I can take x to be direction 1, y to be direction 2. Of course, z to be direction 3. So I'm not going to worry about it right now. Fine. So wherever there is x, I'm going to put it as 1 now. So what I get is dou sigma 1 by dou x. So dou sigma 1 by dou x, I'm going to now write it as sigma 1. If I put a comma, it means dou by dou. Okay, comma 1. Is this Clear to you? Number one, I'm going to substitute anywhere I have x as 1 because it's just an index. And if I have dou by dou x, then I'll put a comma and then put a 1. Okay. If I do this way, what I will get is this one will become sigma 1, 1, comma 1, 1, 1, comma 1, plus instead of tau, I will write it as sigma itself because it is after all stress which is having the mixed indices here. Okay. Sigma 1, 2, comma 1, 2, comma 2 plus B1 is equal to 0. Are you able to see this? Yeah. Now, what you see over here is sigma 1, 1 here, sigma 1, 2 here, and B1 here. So there is this index which is common, and there is an addition that I'm seeing over here. So I can now write it as sigma I j comma j. Remember, this is repeating, plus bi is equal to 0. And here it is j equal to 0, I'm sorry, j equal to 1 to 2. The same statement I have written here. No difference. Are you able to see this? Yeah. Now if I say I is equal to 1 and 2, then I take care of this also, if you notice. Yeah. So when Einstein was writing this, he said, okay, anyway, if I have repetition of indices, I'll just remove this fellow and write it like this. Okay. If you are not very conversant, you can put it as sigma. Okay. Sigma j equal to 1 to 2. Okay. But this is the equation of equilibrium I get. Remember, this is the partial differential equation I get. Okay. It needs boundary conditions also. Okay. So what I get basically is if I have a continuum here and I'm looking at equilibrium of a point P here, this is what I get as equations of equilibrium. So far so good. Any questions? Very simple, but powerful at that because I've used the concept of continuum here, that there is a continuity that I take care of. Okay. Now, Dirac as such gave us a little bit more power. He said, okay, if there is something that is not continuous, you take it as Heaviside function and continue to take the derivative. So no problem. I can do the integration, etc., etc. As long as integration is over there, there is no problem. Okay. I'll do that exercise as far as when we come to bending, but here let's assume that it is the stress is continuous. More a better thing would be that it is at least once differentiable. Okay. Can you explain why second term is sigma 1, 2, comma 2? Yeah, sigma 1, 2, comma 2 is this is sigma 1, 2, comma 2 only, no? Sigma x is 1, y is 2, this y is 2. Chaitanya. Why that?
He just confused with you. Replace sigma with tau. Sorry, tau with sigma. So that's why.
Is now right. Okay. Is tau right? I'm not able to understand Chaitanya.
He's asking if sigma 1 2 is tau only.
Sigma 1, 2.
Yes,
sigma,
it's tau.
Yeah,
only,
this is tau. This is tau only. Yeah, this is tau
it's
only.
part,
But
yeah.
it's a stress, no? So whenever I have the mixity, one x and y, then I called it as tau earlier. Okay, now I'm coming back saying, okay, I'll use sigma itself. Okay, just for making sure that this is short. That's all. Thanks, Darwin. That's all. All right. So take it as sigma 1, 2 means tau 1, 2. Okay. Is this clear? Very simple. Again, once you get this partial differential equation and the boundary conditions, it should be possible for us to solve for what would be the stress field in a continuum or in a body which has continuum in it. Okay. If there are no questions, I have to move on. If there are no questions, I have to move on. If there are questions, then I can remain over here. How do you now change it to 3 dimensions? How do I now change the dimension? Oh, that's very simple, sir. All you do is put a 3 over here and put a 3 over here. How about that? Very simple, right? 1 dimension, no problem. I just make it a 1 here. I just remove this 1 dimension, right? So there's a very powerful and very simple way of writing this. Okay, we usually write in continuum mechanics. We'll just write it as sigma ij comma j plus bi equals 0. That's all. This automatically means that j goes from 1 to 1, 2, and 3, and this is a summation index because it is repeating. I goes from 1 to 3, which means there are 3 equations that I can write. Okay, but don't worry about this if it is confusing. So I'm just going to erase this. Okay, and this is basically the 3 equations that I can write. Okay, all right. I'm going to erase this. Okay, so we have now completed as far as stresses are concerned. We looked at stresses. We looked at how we write stresses for a single point. We also looked at how to transform, right? And then we got some understanding of the stresses after transformation, the Mohr circle, right? We also looked at, okay, how I can use stresses to find out failure has occurred so that failure can give me an idea of strength. Also, I can write down the equilibrium equation for a body where the point lies, right? That's what we have done so far. That's not enough though. I'll tell you later about why it is not enough. We also have to look at how the body has deformed. Okay. Remember, this is a deformable body. Okay. So a body, if I take a body, the body might probably deform from, so let's say the same point P here would have deformed and moved, right? This is a different shape that it has taken while some forces are acting on that. Okay. We wish to find out what? We wish to find out how the body has deformed. That's the question we want to ask. Okay. And this question, I'm going to make it a very simple question. You can complicate to the extent possible, but we're going to make it very simple from whatever our understanding has been in terms of elongation in 1 dimension. Okay, what did we do in 1 dimension? Let's say I have here, let's say this is x direction. X direction, I have a string or 1-dimensional body, and if it elongates by an extent, and let's say this length is L, this is delta L, then epsilon, which is strain, is given by the ratio of the extension divided by L. Right? This is what we did. Right? Since it is in the x direction, I can call this as epsilon x. Okay. So far, so good. Is this clear? Now, there are 2 things to it. One is the body is in the x direction. Is in the x direction. What do I mean by that? If I take a small portion of this, okay, which is, let's say, delta x I take, okay, and this extends, all right. This extension divided by delta x will give me epsilon x, okay. This is delta x. The elongation is also in the same direction. I'll repeat it once more. This body is a line in the x direction. The body is a line in the x direction and it is elongating in the x direction, which means there are two x's I am using. One is the body, which is a line in the x direction. The other is the elongation that is along the x direction. And therefore, I should put it as epsilon x, which is the first one representing the line that I have taken in the body. And the next one is which direction the elongation has occurred. Or in other words, if I have a line that I have taken over here, which is dx, and I'm looking at the strain in the direction that is along this, then what am I looking at? I'm looking at epsilon x. Is this clear to you? Very simple idea. This becomes powerful because if I need to have strain in any other direction, I have to do exactly the same thing. For example, how do I find out epsilon YY? What do I do to find out epsilon YY? Again, one more question. What do I do to find out epsilon YY? Having understood what is epsilon XX, how do I find out epsilon YY? This is the body that I have. Go on.
So along y we will take the
Come again.
so like along y we will
What do we take? Yeah, but before movement, I want you to locate it. There are two y's here. There are two x's here. A wise person will look at two y's here. What do the two y's represent?
Sir, one is phase and the other is force, sir.
No, that is for stress. What did I do here? This will give you a clue.
One is the length along y-axis and another is the elongation along the y-axis.
Exactly. See, I picked up a line element. I'm going to call this as line element. Okay, which is along the x direction, and noticed what was happening to that line element. Okay, so the line element was going like this. It had an extension. So this was dx and it had an extension. Okay, right? That's what I did. Supposing I want to find out epsilon y, what would I do? That's the question I'm asking. Go ahead, Chaitanya. I would pick up.
Who would want to know the length along the y-axis?
Wait. I would, yeah, exactly, Karthik. I will consider a line segment along the y direction, infinitesimal line segment along the y direction. That's the first thing, so which means I have fixed this y. Then I ask the question, what would be its extension in the y direction and or the ratio of it, okay, and therefore the next y direction. Clear, Chaitanya? All right. So if I do that, I'll be able to get epsilon YY. Okay. So in other words, if I have taken a rectangular box like this, extension that happens in this direction will be connected to epsilon XX. Extension that happens in the y direction like this is connected to epsilon YY. But there is also epsilon. If I have to extrapolate, there is also epsilon XY. What shall I do? What shall I do? Epsilon XY, what shall I do? So for that, I'm just going to show you So what I have done here is I've taken an arbitrary body. Okay. So just for your uh, visual effect, I'm going to do this. Give me a second. No? I now have an arbitrary body. Arbitrary body. Are you able to see? Okay, I have drawn the line elements. Okay, let's say this is the x direction, this is the y direction. Okay, so as it deforms, you can see all the squares are there, but they have become rectangles, right? But they have also sort of instead of rectangles, they have now become
Parallel.
parallelograms, right? Parallelograms, right? And that's what I have to describe. This is a more general deformation that I can see, correct? Right? I want to represent this, and let's say each of these squares represent a point. Okay, you can think of since you are able to see, it's fine, but you can think of each of those squares to be, or square or rectangle to be nothing but representing a point. Okay. Or you can do one thing, which is you can take the lines in the in the in the x direction. Okay, I can do this in the x direction and y direction. Okay, and ask the question: how are the line elements stretching? Is one question. The other is, while it was perpendicular initially, right? It was perpendicular initially, right? After deformation, they seem to have lost the perpendicularity, correct? And this concerned the tendency of what was y to be moving in the x direction, what was x to be moving in the y direction. So far, so good. Is this clear? So, if I ask the question, what is epsilon xy? What is epsilon xy? Then I'll say this is the line element, and this is the movement in the y direction. For example, if this is the line element I have picked up, which is along the y direction, let us say it has moved like a parallelogram to this, right? This movement has to do with epsilon xy. Is it epsilon xy? Epsilon yx. Fantastic. So this is epsilon xy. Epsilon yx has to be like this, correct? So that if I do like this is the x element that I've taken. This x element is now, let's say, rotated like this. Okay, and this movement is related to epsilon xy, and this is related to epsilon yx. Okay, right. So I have now taken the elongation in this direction, also change in the angle between them. So initially it was pi by 2. Now it has shifted. Okay, so this is one angle, this is another angle, right? The total angle that has changed is, I'm going to call this as some gamma xy. As you can see here, gamma xy is nothing but the addition of these two. Okay, so I'm not going to call it as epsilon xy and epsilon yx here. The reason is the following. I want you to be very notice very carefully. Okay, just notice this carefully. I started with a body which was rectangle. Now it has become like this. Now it has become like this, right? This is one angle that I have. This is the other angle I have, right? Initially, it was perpendicular like this. Now it has changed in angle. I can always rotate this fellow and make it into something that is like this. Can I not? Take this diagonal, I rotate it, so this coincides with the x-axis. Now what do I have? I have this total angle, right? I can do the similar way by rotating. And rotation is a rigid body motion, correct? It does not have any deformation, right? Agree with me on this? And therefore, I don't want to distinguish between this and this. I'll put them together and call it as gamma xy. So the angle that has happened, this total angle change is gamma xy. Either you want to align it with x or y, it does not matter. Because that's just a rigid body rotation. I'll just ignore that. So far, okay? Is this clear? In that sense, I will say this is equal to epsilon yx is equal to gamma xy by 2. I'm just equally dividing between the two. If this idea is clear, you learned something on strains today. If you have a question, you have to ask me now. Thanks, Kishore, for identifying. If you have a question, you have to ask me. And therefore, let me erase this. And therefore, now it's becoming clear to me. I can now write a matrix with all this. This is for the element. So element X. So this is element, line element. Okay. I can take line element X. I can take line element Y. Right. I can take movement in X direction. Movement. Shall I say stretch so that it's clear? Change. Okay. I'll use change. Okay. Change in X direction. Change in Y direction. And say, okay, if I have X element taken and there's an elongation in X direction, then I'll call it as epsilon XX. Similarly, Y element Y change as epsilon YY. And if there is an X with a change here, I'm going to now change it to gamma XY by 2. Gamma XY by 2. Okay. Or I can write this to be epsilon XX, epsilon XY, epsilon XY, epsilon YY with epsilon XY equal to epsilon YX. Remember, I have enforced a symmetry over here. Okay. This is the way I can define the strain in the two-dimensional body. Okay. And remember, this is pertaining to a point P. And this point P I can blow up. It seems to have one length this way and another length this way. Okay, so I can take this line element for considering this line element for considering this. Okay, so I've just done this. You can see it now. This is this. Think of it like this. I have a reference frame for which the body now initially has a perpendicular line elements dx and dy. Okay, after deformation, this has stretched and this has stretched, not only stretched, but also the angle has changed. Okay, with this, now I can do many things, but right now I will consider primarily that I have these strains available now. Got it? All right. Now this is nothing but the strain of point P, correct? So this is the strain of point P. Along what directions? X and Y. Okay. So uh, I'll put P inside so that, okay. And this is nothing but epsilon XX. So I can now write this to be epsilon ij, where I is X or Y, J is X or Y. Okay. This is in a matrix form. Okay. Now you can ask the question, okay, what if it is a line element that I've taken along this and along this, which is X prime and Y prime? What would be your answer? What if I take along X prime and Y prime as line elements? So basically, I've now taken a line element that is like this and like this. I will get what? Epsilon X prime, epsilon Y prime, tau, I'm sorry, gamma X prime, Y prime, correct? Right? Without much thinking, it's now clear to you that I can transform. So this is with respect to XY, right? I can also transform and write the same strain about X prime, Y prime to be nothing but epsilon I prime, J prime matrix. Is this clear to you? It's the same strain, but with respect to X prime, Y prime. This is with respect to XY, and this is with respect to X prime, Y prime. And if X prime, Y prime and X are related, then just like what I have done for stresses, I should be able to transform these. So what shall I call this quantity as? As a tensor. Fantastic. So now we have recognized one more tensor, which is a strain tensor. So today what we learned is a strain tensor. Okay, this is pertaining to point P. Clear? This concept is very important. Whatever we did today is very important. Please review. Okay. We are going a little faster, but for a reason, I'm going a little faster. Please review. Okay. All of you. That's my earnest play. Any questions? Any questions you may have? You can ask now. Open your camera and ask if you have a question. Discussion can happen. Discuss ion can happen. No discussion. Okay. Okay, folks. Enjoy the weekend. We'll meet on Monday. Bye.
Yes.
Bye. If you have any questions that you're not able to ask, send it through WhatsApp.